Every transformer you have ever used carries a quiet tax. As the conversation grows, it stores a key and a value for every single token in something called the KV cache, and that memory just keeps piling up. Longer context means more to hold and more to compute, so generation gets slower and pricier the further you go. What if a model could keep its memory a fixed size, no matter how long the input ran? That is the promise behind Mamba-3, a state space model from Princeton, CMU, and Together AI. Let's unpack how it works. First, let's look at the core swap this model makes at the very heart of the network. This is how a transformer remembers. Attention lets every new token look back at every earlier one. And to do that, it caches a key and a value for each token it has seen. That KV cache grows with the sequence. So a long context eats more and more memory, and each new token costs more to generate. The quality is excellent, but the price climbs the longer you run. This model takes a completely different route. Instead of caching every token, each layer keeps a single fixed-size state that compresses everything it has read so far. Reading a new token updates that state through a recurrence, so the memory stays constant no matter how long the context grows. The team reports matching strong baseline perplexities while decoding at roughly half the cost. So how does Mamba-3 actually move through a sequence? Follow it one token at a time. Every step starts with the next token arriving. There is no lookup across a growing cache and no attention matrix to build. The model simply takes this one token together with the state it already carries, the compressed summary of everything that came before. That single state is the entire context it needs to move forward. Now the state gets updated. The token is folded in using a refined discretization the authors call exponential trapezoidal, plus complex valued updates that act like a data-dependent rotary embedding. That rotation lets the state track order and structure far better, enough to solve parity tasks that earlier Mamba models essentially failed. The state changes, but its size never does. Once the state absorbs the token, the model reads an output straight off it and predicts the next token. Because everything it knows lives in that fixed state, generating one more token costs about the same whether you are 10 tokens in or 50,000. Compute stays linear and memory stays flat. Here's where it pays off. A transformer slows down as its cache swells, but this recurrence just keeps stepping at a steady rate. At the 1.5 billion scale, the authors report lower perplexity than Mamba-2, 10.35 against 10.47, while decoding long context far more cheaply. Strip it back, and 3 ideas capture why Mamba-3 matters. This is the heart of it. Where a transformer stores a KV cache that grows with every token, Mamba-3 keeps a single fixed size state per layer. Memory stays constant and compute stays linear, so cost no longer balloons as your context gets longer. That is the whole reason state space models scale to long sequences so gracefully. Now the payoff for quality. Matching a transformer used to be the hard part for recurrent models, but the authors show this design keeps pace with strong baselines and even edges ahead at the sizes they tested. Complex valued state updates and a multi-input, multi-output layout let it retrieve and track state without leaning on attention at all. Here is the honest caveat. A fixed state is a compressed memory, so it cannot recall every past token perfectly the way full attention can, and the reported wins sit around the 1.5 billion scale rather than frontier size. The MIMO variant also raises decoding flops, though the authors say latency barely moves. Promising, but not a finished replacement everywhere. Alright, let us lock in what Mamba Mamba-3 really is. This is a 2026 state space model from Princeton, CMU, and Together AI that swaps attention and its KV cache for a fixed size recurrent state. Because that state stays a fixed size, memory is constant, and compute is linear, so cost does not grow as context gets longer the way it does for a transformer. Across the tested scales, it matches or beats strong baselines on perplexity and downstream accuracy, and the team reports decoding roughly twice as cheaply as comparable transformers. Remember, it is still early days. A fixed state compresses the past, and the headline numbers sit around the 1.5 billion range. So treat this as a promising direction rather than a finished transformer replacement. If you enjoy watching fresh AI architectures get unpacked this clearly, come explore the rest of our library over at standari.com.